All right, this example, the way I've got it written, one, it doesn't look like anything related to what we've been doing. Two, it doesn't show up on that worksheet directly, so you might be wondering where it's coming from. So it actually turns out that this is just a rewritten form of the very first example on the second page of that worksheet I've posted. Because if you remember your trigonometry, you can take apart the cotangent function like so. Cosine of theta over sine of theta. Now it looks like one thing divided by another, and hopefully you see where this is going. Let's grab a u out of this sucker. Denominator is our target, sine of theta. The du that goes along with that is cosine of theta d theta. No negative, because we're taking a derivative this time. Cosine of theta d theta. Oh, look, that's handy. 1 over u du. That's a natural log function once we do the integration. And then we undo the substitution, like you do. And yeah, so if you were wondering where that formula for the indefinite integral of the cotangent function came from on the bestest friend sheet, ding, we just got it. So that's that example. It also kind of gives you a way to take care of another problem that talks about a cotangent function further on down the worksheet, so you don't actually need to take this apart. So you're welcome. So a couple more I want to take a look at on here. Board full, you know the score. In case you didn't know the score is fill 1, full board 0. So next example is actually the very last one on the worksheet. I kind of apologize for the way I'm pinballing around these, but you know, I'm helping you out, so stop giving me grief. Anyway, this one is actually a bit clearer than the last one because, well, maybe not based on how it appears on the worksheet, but it's not just immediately like a cotangent function or anything. Grab the bottom. U equals 1 plus sine of t. I also like messing around with this where you have to use a variable that's not x just to keep you on your toes. Again, once you pick a u, du, we need right after that. Oh look, the 1 out front of the sine function has a derivative of 0. He goes poof. We still got exactly what we need. And shock and dismay, we're exactly back where we were in the last problem. Except, yeah. So ln absolute value of u plus c, back substitute. Be careful with your, one. I know if your handwriting is like mine, it's kind of hard to tell a 1 apart from an absolute value bar, so yeah. Anyway, so there we go. So that's that. We finished 2 examples in like 3 minutes. We're like seriously cooking with gas here. Okay, I want to take a look at one more problem now. Actually, the one in the middle. So again, razzmatazz, get rid of board stuff. So let it be done. All right, so like I said, I was grabbing the middle example here. I like bringing this one up because you can kind of get into a rhythm that can mess things up when you're playing around with these. So this time around, it turns out the thing we're going to want for our substitution, it's in the denominator, but it's not really the whole denominator, because you can see here, if we grab this entire thing, we've got this cube as well, right? And then, we need the chain rule for our du, and yeah, you might be able to there's actually a way you could make it work, but it's going to be kind of a pain to maneuver through. So this time around, let's be a little bit slick and say, well, we have some stuff in parentheses. As we've said before, stuff in parentheses kind of jumps out as a likely target. So x cubed plus 3x squared. All right, again, once we get a u, find the du. Well, we get 3x squared plus 6x dx. And you may notice at this point, hey, look, in a miraculous stroke of plot convenience, we have x squared plus 2x up in the top of this thing. If I factor a 3 off here, that's an x squared plus 2x, right? So yeah, so 1/3 du is x squared plus 2x dx. So that's a thing. Now, this whole thing becomes, well, I'll write it sort of the naive way, and then we're going to do something. Okay, so we have 1 over u cubed times 1/3 du. Okay. Now, that's fine. If you written the 1/3 out front, I just about did, so also fine. The catch is, here's another place where students will sometimes trip up over things like this, because you really get into this rhythm of the denominator. If I've got like a division thing, I should have some kind of natural log function that appears in my antiderivative. Yeah, here's the catch. Is that 1/u? No, it isn't. It's 1/u cubed. I mean, I guess theoretically you could try to ramrod in another substitution. Don't. So just as a heads up, and let me go ahead and pull that 1/3 out front. So yeah. Anyway, so 1/3 get out front. Remember, we don't have a quotient rule or anything like that. This isn't 1/u by itself. That means the natural log is off the table. This is u to the -3rd power if we pull that guy back up to the top of the fraction. We don't need the natural log here. Our regular old power rule applies to this thing. So add 1 to our exponent. That gives me -2. Remember, adding 1 to the exponent here gets it closer to 0, not more negative. With plus c, we divide by this new exponent. So we got a -1/2 right there. So yeah, these guys multiply together, -1/6, and I need to plug u back into this thing. X cubed plus 3x squared to the -2nd, plus c. If you wanted to untangle it and write it as a rational function again, you can do so, feel free. But the calculus is done at this stage. So yeah, so I just wanted to make sure you were sort of on guard about this. Just because there's a denominator doesn't automatically mean you have to find some way to make a natural log show up in your indefinite integral. So we've covered most of the tricky bits that I wanted to take a look at in this final worksheet. We're not quite done with substitutions, though. You may recall there's still, an entry in that list of things to pick for you I wanted to take a look at. And there's an example or two in the homework that I think also merit taking a moment to look at. So one more video coming at you.